This is our last lesson for Unit 5. This video is going to be talking about the limit of a function and going into the existence and continuity of those functions. So getting into it, I just want to go over 3 concepts first that can be kind of confusing to people. Okay, so the first one is going to be, what is f at any x value? So we'll just call it a. Okay, so that's going to be a random number that I'm going to sub into f at x. So I'll talk about the other two later on with different colors. Okay, what does that actually mean? Well, if let's just say a is 4, we're going to figure out what the y value is, and that's pretty easy. You're just going to extend this and be like, okay, there's a point on the function, and I'm going to go across, and that looks like it's about, I don't know, 5.9, maybe 6. So what you just found out is if I decided to sub in 4, I'm going to get a y value of 5.9. Okay, let's get into the next one. So what exactly does this mean then? Well, we'll use the same a value and just say, if I'm taking the limit as x approaches 4, I'm not talking about where the function is at 4. I want to know what happens when we're approaching 4. So what that means is, instead of going, okay, I'm looking for this dot, I'm not. I'm actually looking at what's happening to the function as it gets closer and closer from either end of that dot. So both of those orange arrows seem to be approaching the same dot, and that dot has a height of 5.9. That means that the limit is equal to 5.9. And you're going to be like, aren't they the same thing? Like purple and orange looks the same. No, not really, because the purple is talking about the dot itself, and the orange is talking about the two approaching arrows. Okay, so we're going to be talking about both a little bit more later. Now the last one. This guy right here, we talked about in other videos, where the numerator looks like delta y. So it's like your y values subtracting each other. That's your rise. The denominators are your x values subtracting each other. So that's your delta x. This is your run. Now obviously when you take your rise and you divide it by your run, that gives you your slope. Essentially what the limit of this function or this equation means is, let's just pop back that point. What this means is, tell me what the slope of the tangent is at that point. So there are infinite number of tangents all along. So I'm going to draw a couple right now. Okay, I'm not doing this very well, but do you see how they're like just skimming that little hump right there? Well, it's going to skim this one point right at that one unique tangent, and I want to know what is the slope of that tangent. That's what this one is saying. So let's get into some more examples and you'll kind of see what happens. I'm going to be doing a lot of examples based on the orange though. That's what we're going to be talking about mainly in this video. Okay, so determine the limits for the following. Notice that this is not saying x equals to 2, because if it was saying x equals to 2, we would literally just figure out what f at 2 equals to and put 2 into our function and solve and get 3. Okay, so that's not exactly what it's asking you to do. What it's asking you to do instead is it wants to know you approaching 2. Okay, so when you're approaching 2, we're talking about the orange. We're talking about those two arrows that are approaching on the left hand and the right hand side. So I have my 2 right here, and why don't we start to approach 2 from the left hand side? So I'm going to start approaching from the left hand side, maybe at something like 1.9. That's pretty close to 2, but is on the left hand side of the number line of 2. So I'm going to start to create a table where I sub in a lot of points or a lot of values that are getting closer and closer to 2. Okay, now when I did that, all I'm going to do is I'm going to sub in those numbers wherever I see an x in the function, and I'm going to calculate my answer. So 1.9 squared minus 1 It's going to give me 2.61, and then 2.96, and then 2.996. Okay, so it looks like in this case, as my x approaches from the left-hand side, that's right, when we put the negative up there like an exponent, that means 2 from the left-hand side. Our y seems to be approaching, like it's getting closer and closer to like 3, right? 2.996 is pretty darn close to 3. Let's do the other arrow, the one that's approaching from the right-hand side. So I'm going to approach from the right-hand side, and 2.1 looks like a number on the number line that's like pretty close to 2, but it is to the right of 2. So we're going to go x and f at x. Does this look familiar? Like this stuff should be from advanced functions, I think. Okay, so 2.1, maybe 2.01, 2.001, and so getting closer and closer to 2 from the right-hand side. I'm going to take each of those values and again sub it into my x value. So 2.1 squared minus 1 gives me 3.41. And then these are the other ones if I start subbing in these x values. So you'll notice that as x approaches 2 from the right, we put a plus to indicate that we're coming from the right, y appears to be approaching 3. Right? Like it goes from 3.41 all the way to 3.004. It's getting really close to 3. So we've analyzed both of the arrows from either ends, from the left and the right, and it looks like they're both approaching 3. So that analysis is pretty important. And this is what I'm going to write. I'm sorry, I'm going to extend this a little bit and then just backtrack a bit. Smartboards like that, it jumps. We just did something called the left and the right hand limits. So this is the left hand limit. That was the blue. The green was the right hand limit. Okay, so if I were to write it without the tables, it would look like this. The limit as x approaches 2 from the left for your function, but we actually know what our function is, so we should really write our function. X approaches 2 from the left of x squared minus 1, that was our function, is going to be 3. Okay, now you don't have to do the table. What you can do is you guys can just take numbers that are like really, really close to 2 from the left and sub them in and see what it gets really close to. Okay, so it gets really close to 3. Don't just take 2 and sub it right back in, because again, that's what we said we weren't supposed to do, right? So don't just take 2 and sub it right in. Okay, now the right-hand limit was the limit as x approaches 2 from the right-hand side of f at x. Again, we know what f at x is, so we should write it. 2 from the right of x squared minus 1. And if you take numbers that are super close to 2 from the right and you put it into here, you don't have to do the whole chart, okay? But you can do it on your calculator, just randomly punching in numbers. You will get really close to an answer of 3. Overall, it looks like from the left hand and the right hand side that when x is getting closer to 2 from either side, your function is actually getting closer to a y value of 3. The overall rule that we're going to say is the limit is the same. Sorry, if the limit is the same from the left and the right hand bounds, okay, we can say that the overall limit from x approaching 2 from the left or right, so I'm not even going to write that, of your function is equal to 3. Okay, now you're going to be like, okay, so what happens if you get a 3 and this one is not a 3, this one is like a 4? Okay, if they don't match, then you would actually say the limit as x approaches, 2, of your function does not exist. Because they have to actually match from both sides. If your arrows are approaching different places, obviously your function is not continuous. We're going to get into a little bit more of that in a second. Okay, so let's try some more questions. Example number 2. So again, I don't want to find the purple where it's just x equals to 1 and sub in a 1 right away. That's obviously a problem because if I sub in a 1 right away, like it doesn't even exist because the denominator is going to be a 0. So we're not doing that. What we're going to do is we're going to start testing the left and the right hand limits. So I have both of the tables. They kind of help me out. Depending on how your teacher likes it, you can either show it or you don't have to show it because you can do a lot of this on your calculator. So I want to know what the left hand limit is like. And so I'm going to start to take numbers from my, let's see, my 1. So let's just put a 1 right here. Okay, and the blue is going to be numbers that approach from the left. And so I'm thinking 0.9 might be the first one. 0.99, 0.999. Okay, and you're going to be like, why do you even have to do the 0.9 or the 0.99? Why don't you just do the 999? That's a very good point. And you asked some darn good questions. I'm going to move on. So sub in those numbers, 0.9 into these two first, and calculate your answer, 1.9, 1.99, 1.999. So it looks like as x is approaching 1 from the left, y is approaching, it looks like 2. Okay, so this guy is going to equal to 2. Now, if we're approaching from the right-hand side, okay, right-handed numbers 1.1 might be something I want to start at and then go even closer and then even closer. Now, subbing 1.1 into both of these and calculating my answer, I get 2.1. And then doing the same thing, 2.01, 2.001. Also looks like as x is approaching 1 from the right-hand side, y is getting closer to 2. And so the answer to this is 2. Now that you've tested the left and the right-hand side, and they're both the same, you can say, since the limit as x approaches 1 from the left of f at x is equal to the limit as x approaches 1 from the right of f at x. Therefore, the limit as x approaches 1 of f at x from either side exists. Exits, yes, I mean exists. So it equals to 2, which means that it exists. All right, let's keep going because I think we're on a roll. Okay, something really crazy. This is something called a piecewise function. And so notice that this function is made up of 3 other functions. But each of those functions exists in a certain domain. So look at the domains to the right of it. Why don't we try to graph this? Okay, so I'm going to use different colors. We'll say this one is the first one. X minus 1, so y equals to x minus 1 is just a linear. And I would probably draw it like, let's use an actual tool. Okay, so y-intercept, whoa, that's not what I wanted to do. Y-intercept at -1, slope of 1. So this line goes like this. Let's make it purple. And I actually want to show you that it's only going to go in one direction because take a look at, let me see, it said right here. Just take a look really quickly at the domain. So the domain had said only from -infinity to 1. So 1 is right here, right? And that means that I'm only going to draw it with one arrow that's going in the -infinity direction. But also notice that we have a round bracket, which you guys should have learned last year or last semester, whatever, whenever you did advanced functions, that doesn't include 1. And so I'm going to put an open dot. Let's try the next one. Okay, so I'm going to draw this function in orange. Y equals to 1. Okay, y equals to 1 is like a function that just goes straight across 1. But the domain is x equals to 1. Okay, so that means that there is no function anywhere other than an x value of 1. Let's get rid of that. We'll also get rid of all of this. And that's it. You have a point right there at 1. Okay, and 1. All right, so that function actually is only one coordinate. And it's a closed dot because they actually said it equals to 1. So the last part of our piecewise function, it looks like a root graph. Okay, so a root graph starts at 0, 0, and then goes here, and then hits here, and then hits, I think, like somewhere there. Something like that. Okay, but it looks like there's been some transformations, and so the -1 means it went to the right. The +2 means it went up, and so I'm going to take my function, move it to the right, and up 2. Okay, so there we go. That's my function. Now I'm just going to make sure that the domain is okay. So the domain says from 1 to infinity. All right, I'm starting at an x value of 1, and I'm going to the right with my infinity, right? And it does not include 1. So I'm going to put a circle right there. So anything up to or over 1, up to 1, but it doesn't really include 1. So this is our graphics itself, and what I want to do is I want to start considering x approaching 1. Okay, so let's try that out from the left and the right hand side. So I have that set up in blue and green again. And it looks like if I approach along my function towards 1 from the left-hand side, that would be the purple function, approaching this way from the left-hand side towards 1. That means that I'm going to use the purple function, x minus 1. All right, now what I can do is I can start subbing in numbers in here that are from 1 to the left-hand side, very close to 1, and sub it into the x and see what I get. So maybe I'll try 0.9, 0.99, 0.999, and it looks like what's happening is my x is actually going to start to approach a y value of 0. And that makes sense. Like, doesn't it look like right at this point, what it's trying to approach has a y value of 0? Okay, let's try out the other side. Now I'm going to start approaching from the right-hand side of 1. All right, now approaching from the right-hand side of 1 goes along the other function, because the other function seems to be able to come from the right, going down that way. Okay, so that means we're using the turquoise function, equals the limit as x approaches 1 from the right-hand side of the turquoise limit. Turquoise limit is 2 plus root x minus 1. So we're going to take numbers that are from approaching 1 from the right, which is 1.01, 1.001, and we're going to sub it into there. And you're going to start to see that your y values are going to approach 2. And that makes sense because take a look at the point right here. As this guy is coming down, it's approaching a y value of 2. All right? Now, your blue and your green don't match, so that's a problem. Since your limit as x approaches 1 from the left of f at x, okay, like the whole function, does not equal to the limit as x approaches 1 from the right for your entire piecewise function. That means that the limit as x approaches 1 of the entire piecewise function does not exist. Okay, and that makes sense. Like if I were to ask you, okay, out of this entire graph, what is the y value when x is 1? What would you tell me? Like, would you tell me it was 0? Would you tell me it was 1? Would you tell me that it was 2? Like, it's kind of confusing. Or actually, you know what? I kind of asked that very poorly. What I mean by that is, what is it approaching? Not what is the y value when x is 1? Okay, I'm starting to confuse you. I apologize. Let's try that again. And this is what we do as a teacher. We say things come out of our mouth, and then we're like, that didn't sound that great. So we say it again. There is a difference, just like at the beginning of the video, between f at 1 and so when x equals to 1 and when x is approaching 1. So you'll notice what we just did right here was x approaching to 1, and that did not exist because approaching 1 from the right, approaching 1 from the left, they don't match. Like they're at different heights. In fact, this is called something we call, you can see already that the graph is discontinuous, right? Continuous means if I started from the purple, I would be able to use my pencil and continue all the way along and touch the turquoise in one full swoop. Like I wouldn't have to lift my pencil. But you can already see that there's a gap somewhere here. This is something called a jump discontinuity. And so that means that although this does actually exist, like the 0.11 exists, the limit does not. Okay, so I wanted to make sure that you understood the difference between the two. This guy right here does exist because it's a solid dot. The limit, however, does not exist because they're approaching different heights. I hope that made sense. Okay, so here's the overall general rule. For a limit to exist, you need to make sure that the left hand and the right hand limits are the same. Then you can say that it actually exists. If they're not the same and they don't match, then they don't exist at that x value. Okay, let's go into the last one, and we're going to talk a little bit more about I want to say continuity, but it's continuity, and it sounds so much nicer, continuity. Let's check on this graph this guy, which is the left-hand bound. So as we're approaching 3 from the left-hand side, so we're actually going to go this way, this way, this way, this way, along our function towards our x value of 3. Okay, it looks like it's approaching 5. Yeah, like it's still at a y value of 5. Okay, let's do this one right here. We're going to approach along the function this way, this way, this way, this way, from the right-hand side, and it also looks like it's still at a height of 5. Okay. Doesn't that mean that it exists? Well, there is a problem though, because it's saying that, well, right here, f at 3, so the actual coordinate 3 and -1, is all the way down here. Okay, so what the green and the blue arrow are approaching is actually something we call a hole. And so this guy is a different kind of discontinuity. This one is called a removable discontinuity. Okay, so your function is not continuous because if I tried to trace that dotted green line with a pencil, it wouldn't be able to go all the way across the screen because it would hit that hole. Okay, so it is not continuous. But when we answer the questions, A, does the limit exist at x equals to 3? Yes, it does. It's right there. So there is actually a coordinate at x equals to 3. Now, is it continuously? No. Or is it continuous? No. Because there is a hole. So you can't take your pencil and drag it across on the dotted line nice and smooth. So that other thing that I wanted to talk to you about, which is continuity, is for a function to be continuous, the left hand and the right hand have to obviously match, but it actually also has to match with the coordinate itself when you sub a into that function. So it can't just be looking at the two left hand and right hand bounds and making sure they match in order for the entire thing to be continuous. Because I mean, like, if I go back up and let's say I just move this dot and I put it there, okay, now all 3 of these guys match. That means that I could actually take my pencil and go all the way straight across, and that would be continuous. Do you see what I mean? All right, so let's take a look at our last example. Example number 4. Does the limit exist? Okay, for limit as x approaches 3 for this particular quadratic. Again, we're going to test our left hand and right hand limits. Okay, so I'm going to get 3.61, a little bit to the left of 3, so 2.9. And then 2.99 gives you this y value. 2.999 gives you this y value. And so it looks like as x approaches 3 from the left, y is approaching 4. Now for the green, I'm going to come in from the right-hand side. 3.1 gives me a y value of 4.41. And then 3.01 is matched with 4.04. Then we get 4.004. And that means that we seem to be approaching y equals 4. Sorry, we seem to be approaching 4 for the y value when your x is approaching 3 from the right. Okay, so those match, which is great. But what is the actual point when your x value is 3? Okay, that means we have to sub it in. So that means your x value right here and here will change to 3s. Okay, what is that? Like 9 minus 6 plus 1. That's going to be 3 plus 1 is 4. Hey, okay, all 3 of them are the same. Okay, so we can say that since these guys are equal, then the limit exists. Sorry for the jump. Therefore, the limit as x approaches 3 for your function is equal to 4. Right? They both match, they both approach 4. From what we solved over here, we found that f at 3 is equal to 4. Since those guys match, now we can say, therefore, the function is continuous. All right, so that is our last lesson for Unit 5. Then we're going to get into derivatives, and I keep saying this because they are kind of fun. Like it's just like little algebraic puzzles. It's a lot faster than this limit stuff and first principles. So we're going to teach you obviously the really slow way, and then teach you the fast way and have you guys get mad at us. Okay, so have a great day. See you next time.